Greg actually contacted me and asked me to talk about mass quenching. Unfortunately, some of the stuff is pretty old, and you must have heard it a few times. So I'm just going to go as quickly as possible over that part, and I'm going to emphasize the assumption that actually go into the stability analysis, because I think that, well, it has to do with the third point here. I think that I'm sometimes misquoted. I'd like to set the record straight. It's a good opportunity to do that. Then I'm going to show two ongoing projects which are connected to the whole virial shock stability question. And so let's start. So initially it all started with one-dimensional simulations, spherical simulations. So this is radius, this is time. The lines, the thin lines, are Lagrangian shells that actually evolve in time. So initially they expand, then because there is some initial perturbation, they start turning over one after the other and collapsing into what we called the spherical disk. It's an angular momentum supported region, and there's dark matter as well. We are not seeing it here, but it's in the background. And the whole virial shock question came up from this part over here. So we saw that, the color map is temperature, and it turned out that there was a wide regime where the gas did not pass through a virial shock. So the virial shock, you can see it here, but it's not always there. Not all halos have a virial shock. And it took us some time to understand what's going on, and to really understand why there is no shock here, but there is a shock here. It's useful to just focus around the shock. So let's just focus on what's going on in this little box. So there is a shock, and stuff is supersonically falling through the shock, and then it's subsonically falling below the shock at a much lower velocity, at a quarter of the velocity, because we assume that this is an ideal gas with an adiabatic constant of 5/3. And since everything here is subsonic, we can assume that initially the forces balance out. So the shock would adjust itself so that the forces are zero immediately below the shock. But there is a velocity inwards. There is a big perturbation that the velocity is actually producing, and this perturbation is going to cause forces to come about, and they could either be negative, meaning inwards, or positive. If they are negative, then all the shells here will start accelerating inwards, and the shock itself would accelerate inwards. So the shock would not be able to be stable. If the forces are positive, then a positive halo a hydrostatic halo can form. So we need to assume something. We need to assume something about the velocity gradient right around the shock. We assume it's homologic. It's the most basic assumption we can make. And I just want to mention that this is a very unusual perturbation analysis. It is a stability analysis. We are perturbing the situation, but the perturbation is not general and it's not small. The velocities are large, and they are also very, very specific. They have to do with the Houguenot jump conditions across the shock. So we're not going to get a dispersion relation that connects every type of perturbation to the question of stability. It's a very specific perturbation. And it also comes very naturally, as I'll show you later on, that cooling is very important in the analysis. I'm not going to go over a derivation, don't worry, but I just want to mention some of the key components. So we use an ideal equation of state. P equals gamma minus 1 times the density times the internal energy. The cooling rates are Q. Gamma is defined in the usual way, that's the adiabatic constant. And we also define, it's useful to define an effective gamma, which is not adiabatic, it's the total Lagrangian derivative of ln p to ln rho across a trajectory. And it has to do with the time derivatives, and the time derivative for pressure has to depends on the time derivative of energy, and this is how cooling comes in. So the derivative of the energy is minus P dV dt minus Q. And if we just plug this into here, and this into the definition and so on, we come up with an alternative formulation for gamma effective. These are exactly the same, which is gamma minus rho over rho dot over E over Q. It's sensible because rho over rho dot is a typical contraction time, and E over Q is a typical cooling time. So there is a competition between two time scales here. When the contracting is very fast, this is very small compared to this, and the effective gamma is just gamma. If the gas contracts very fast with respect to the cooling, then you can neglect the cooling and the gas is adiabatic. On the other hand, if the cooling is faster than the contraction, the effective gamma becomes small. It can even become negative. And negative gamma would mean that as the gas is contracted, its pressure goes down, not up. And this is possible for the effective gamma. Okay. So if you just do the perturbation analysis, it's all in the paper, you come up with the net acceleration being depending on some prefactor times this term over here, and and this term basically will decide if the forces are positive or negative, if the acceleration is upwards or downwards. When there is no cooling, or when the contraction is much faster than the cooling, the effective gamma is essentially gamma. So this term is going to go away. And we'll just get that the stability depends on the question if the adiabatic constant is larger or smaller than 4/3. This is expected. This is what we always get in stellar evolution, for example, when we want to analyze if a star atmosphere can be stable or not. It depends on its adiabatic constant. And 4/3 is the limit. If we don't assume that these are equal, we can actually construct a critical value and compare the effective value to this critical value. So effective gamma, if effective gamma is smaller than this critical gamma, then the gas is going to be unstable. This critical gamma, if we just plug in 5/3 here, is 1.43. So a gas with 5/3 adiabatic constant that is cooling is less stable than a gas with an adiabatic constant of 4/3, for example. This is slightly larger than 4/3. The cooling actually makes the gas less stable. Okay. We can check it against a simulation. And so we can take, this is the same simulation I showed you before. These are just the Lagrangian trajectories. And we can calculate gamma everywhere in the simulation. If we don't see a shock there, we need to convert using the Hugin-Yor relation, the pre-shock condition to the post-shock conditions. And the post-shock conditions can immediately give us the effective gamma at this place. We can calculate the cooling there, and we know the velocities there, so we can calculate the effective gamma, and it turns out that the effective gamma is always largest at lower radii. So at this time, for example, the effective gamma is right at the edge of the disk, and we can plot it. So effective gamma goes up, but it's still below the threshold. The critical value is the green line. As soon as it hits the critical value, the shock forms. The shock goes outwards. The effective gamma here is lower than it is here. So the gas here is able to be stable, but the gas here is not. So the gas here loses stability, falls in, and vibrates. It all makes perfect sense. And this is a nice result, basically because there are no free parameters here. We did not add anything. There are no fudge factors. It immediately comes out. And I want to make an important note about it. Everything I showed you talked about the stability of the post-shock gas, which is a precondition for the stability of the virial shock. I did not say anything about if we expect the gas to be hot or cold. So when we talk about cold flows, cold mode accretion, this is not exactly what this means. This is something else. This is just the ability to maintain a hydrostatic halo. And this is important because this gas can get heated up. Feedback processes here could send shocks outwards. Merger could could create shocks sideways, and all these shocks will occur here, but we expect them to fall on a free-fall timescale. So we can have transient shocks, but we can't have a hydrostatic halo. Okay, so this is all microphysics. It's all about shock stability, but we can connect it to the cosmological context. If we just convert the infall velocity and the gravitational term into halos, halo mass, and redshift, we can also plug in metallicity evolution and so on, and we come up with the magic number. We come up with a critical mass of about 10 to the 12 solar masses, that below which we expect a Vier's halo, we expect the halo to be unstable, and above it the halo will be stable. This mass is important because most of the stars form at high redshifts, and at high redshifts, the green lines are the 1 sigma and 2 sigma pressure peaks. At high redshifts, most halos will be below this line. So most of the stars in the universe actually form here, and are expected to form through the cold mode. This is spherical. We can, okay, I'm sorry, one more slide. This is a similar simulation, but for group, for a halo that ends up as 10 to the 13, and this is for a cluster that ends up at 10 to the 14. And we can see that initially, for all cases, there is a stage without a real shock, and it always corresponds to about 10 to the 12 solar masses. Okay. So, talking about the spherical and filamentary nature is similar to talking about the time, the epoch at which we actually want to see what happens to a 10 to the 12 solar mass halo, because at high redshift, a 10 to the 12 solar mass is a high sigma peak, and it will be at the intersection of the cosmic web. It will be fed by many thin filaments. At low redshift, the same 10 to the 12 solar mass halo will be a regular galaxy somewhere along a filament, and it will see a much more uniform accretion onto it. And if we just draw a circle, we do expect at high redshift very non-uniform accretion. So we could have a stable shock when in solid angles where there is no filament, but at the filaments the density is higher, the cooling rates are higher, and we'll get streams penetrating through the hot halo. And this is why there is another regime which is above the critical mass, but at high redshifts, so the filaments are much denser than the average density, and we still expect gas to be unstable within those filaments. So this region over here is what people usually call high redshift cold flows. These are thin filaments punching through the hot stable halo. So people have shown it in many simulations, some SPH simulations. The first one was by Dushan Keresh, and he used an SPH code, free SPH, and he was able to, because of the Lagrangian nature of the SPH simulations, he was able to trace the histories of particles that end up in the disk and check if they were ever heated above some threshold temperature, and to construct the cold mode fraction versus hot mode fraction in the simulations. And it does find that the transition always occurs at about 10 to the first solar masses, and the transition becomes sharper at lower redshifts, where we actually have a spherical, a much more spherical situation.
If you define that transition as being 10 to the 4 Kelvin instead of something like 3 times 10 to the 5, it's much less sharp, is it not?
Yeah, I'm going to talk about it. Ask me again in a few slides if you're not satisfied. And it's also been done with Eulerian simulations. It's tougher to trace particles in time because there particles in our simulations. This is grid-based with flows, but we do see some markedly differences between high redshifts and low redshifts. So this is density, this is redshift of 4, this is 2.5. The accretion here is much smoother than here. Here we can see filaments penetrating through the hot halo, and here the halo is either completely cold or completely hot. These are simulations by Pierre Oswig. Kartso has papers along this line. Agertz has papers along this line, and so on. It has been extensively shown. I just mentioned that. Actually, I'm going to skip it. This was just, sorry, building up tension. This was I'm just making a point here that these stream instabilities could cause extremely high accretion rates. They are the cause of most star formation in the universe. Just if we convolve these findings with the Madao plot, for example, we see that most of the stars will form in these areas, in halos which are expected to be unstable. This is also shown in simulations, and some of the most luminous objects in the universe are due to these stream instabilities. For example, there's a Nature paper, and Avishai Dekel, my advisor, is always good at giving stuff names. So this is the star-forming galaxies, and most of them, and the star-forming galaxies are expected to be due to the cold flows, or the stream instabilities, as I want to call them now. So this is my rant. This is why I think that I'm being misquoted. And it has to do with semantics, with definition. So the term cold flows was coined by Dusan Kerech. And what he did was actually trace the history of particles and check if they were ever heated. But this is not what the analysis shows. This is not where the magic number comes from. The magic number, 10 to the 12th solar masses, comes from the stability analysis, from checking if the gas is never hydrostatic. And another way to do that is what the Eulerian crowd is doing, which is look at a snapshot and see and check if the gas is hot or cold inside the halo at a given time. And the first one is important if we actually want to trace the accretion rates onto the galaxies. The second is important if you want to check the observability of cold flows. If you want to see how much cold gas is expected for some halo at some given time. The third one is very natural for Lagrangian simulations, but I don't know exactly what it represents. And because even if the gas does get shocked, it does not mean that it doesn't fall in on a free-fall timescale, as I showed you before. And okay, so this was my rant. Okay, I have a few cool and interesting projects I'm working on right now, and I just want to advertise them. One of them is the Kelvin-Helmholtz stability of cosmic filaments. So if you look at cosmic filaments, there is obviously a lot of shear. So the gas here is stable and static. The gas here is unstable and going. And we expect Kelvin-Helmholtz instability. And it has to do with the question of how these filaments break at the end. So we see them going in, and at some point we see them basically start breaking down, but we don't think that this is due to Kelvin-Helmholtz instability. We think that these are filaments smashing into each other and other messy processes. These filaments seem to be quite stable, and it's interesting to try and understand why. So some typical numbers. This is led by two students, Neil Mendelkar and Dan Padnos. Some typical values for the filaments. The filament is going to be cold at 10 to the 4 Kelvin. The surrounding temperature for a 10 to the 12 solar mass halo, it depends on the redshift, but 10 to the 6 is a sensible number. the pressure in the hot and the cold, in the hot component and the cold stream is going to be the same. So the density ratio is going to be 1 over the temperature ratio. So expect a density ratio of 10 to 100. The stream velocity is about Mach 1 with respect to the hot component, which means that it's going to be about Mach 10 or so with respect to the cold component. So this is a situation where we have a flow which is transonic with respect to one component of the Kelvin-Helmholtz and highly supersonic with respect to the other component. And it turns out that this hasn't been examined that closely before. And these are some simulations. So this is for Mach half and over density ratio of 2. So this is sort of the uncompressible case you all know from high school. And for a
Israeli high school. Yeah, right.
and for supersonic, for the supersonic case. So this is Mach 5 with respect to the hot component and Mach 15 with respect to the cold component. What we get is a completely different picture. There is no instability that's forming at the edges, and this has actually been known, that for the supersonic case, Kelvin-Helmholtz does not develop. What we do see is a breakout that has to do with modes going throughout the geometry, from one side to the other of a slab. I did not mention it, I'm sorry. This is not a stream, this is a slab. We're in the process of doing the same thing for a stream.
How do you decide the thickness of your slab?
Sorry?
This must depend on the thickness of your slab.
It does depend on it.
Right.
So the parameters were chosen, so the relative width of the slab with respect to the box would be roughly the relative width of the stream with respect to the real radius.
What if the stream fragments into smaller things that you're not resolving?
We've checked for convergence, and it's a good question. It is converged, by the way. Okay. So there is, this is a map of what we intend to do. There is a non-compressible and compressible cases. So this is the supersonic flows, planar, slab, and cylinders. This is in Landau-Lifshitz, or your favorite high school book. This is sheet instability, for example, which is expected to be subsonic. And here we have filaments in relativistic jets. They are opposite to each other. In relativistic jet, the hot component is at the center, and the cold component is at the side. But this is still relevant. There is a lot more. There is some work about this, but no work about this. And we are in the process of constructing the actual analytic stability analysis for all this. So stay tuned. Okay, I'm about to be. Come on, it's one more slide. One more slide.
One more slide.
One more slide. The same charade we did for halos, we can do for filaments and for sheets. So filaments and sheets do have a virial shock at the boundary. And this shock is always more stable than the one for halos, because the geometry, the convergence is less strong. And this is the general stability criterion for one-dimensional, two-dimensional, and three-dimensional inflows, and we can construct an analog stability criterion depending on the cooling rate and so on, exactly like we did before for these cases. And what we find is that filaments, for example, with gamma of 5/3, are not always stable. We don't always expect the gas to get heated and shocked at the edge of the filament. It will sometimes fall inwards, just like for the hydrostatic case. And this is really my last slide. There is a wide range of instability for filaments as well. Filaments with mass between 10 to the 11 solar masses per megaparsec to 10 to the 12 solar masses per megaparsec are expected to be unstable, and we don't expect to see hot gas within this filament. Okay, so sorry for taking too much time, and thank you.
So
So we have time for one question. Christoph.
So on filament instability, is this related to Dirichlet instability?
To,
Dirichlet instability.
no, it doesn't. It's exactly the same analysis as I showed before. The Vishniak is,
Vishniak is ram against gas pressure.
sorry?
Yeah, but this is basically what seeds perturbations, right? I mean, these are sinusoidal perturbations at the SLE interface.
No, it's not sinusoidal perturbation.
Well, I mean, you can answer this different. Okay, so it's,
Let's discuss this. I'm not exactly understand. I didn't exactly answer the question. Let's talk about it later.
Julian's still getting set up. Did you have?
So the filaments are self-gravitating and your hydro experiments don't have self-gravity.
Yes,
That's known to suppress the Kelvin-Helmholtz instability.
that's true. This is Ramses. We intend to edit at some point. That's a good point. We did not introduce it yet.
Well,
if you include magnetic fields, actually the interface, they also actually suppress the Kelvin-Helmholtz instability.
Yeah.
So that's also well known now, and that this is also a natural response in these cases if you actually have filaments passing through these.
Yeah, there is magnetic drape. There is a magnetic draping effect.
Yes, exactly.
It's not clear to me how much, how magnetized is informing material.
Doesn't matter. The draping energy density is actually equal to the ramp pressure. That forms actually hydrodynamically. So irrespective of the magnetic pressure, the end result will be that there's a strongly magnetized sheet surrounding those sheets, irrespective of the magnetic field.
Thank you. That's a good.
thanks, speaker.